If it helps, it helps. Uh, we don't need this anymore. So this whole lateral spreading problem started to happen. अरे यार छोड़ो, it'll be fine. हाँ, जो करना है बाद में करना. When you have sloping ground, say that is the bedrock, and this, let's say, is the saturated loose sand, and this is clay. So this problem was huge in Japan, where surfacial crust, they had clay and some saturated sand. Now this slope angle can be very shallow. This angle, say if I call it beta, could be anywhere from 3 degrees to 10 degrees. So 3 degrees slope you normally cannot detect by eye. If you walk onto the ground and if the ground is sloping at 3 degrees, we'll say, human eye is not very good at detecting slopes, especially shallow slopes like that. So everybody thought it was all great, and then when the earthquake happened, obviously this stuff liquefied and moves along this direction, but as it does, the clay also goes for a ride with it. Now the problem is, if I then imagine I got a pile going through here, I'll get some amount of lateral pressure on this. That's the first problem. How do we estimate that? And more important than that is this clay. Now suppose this clay has, say, undrained shear strength SU of 50 kPa. Yeah? So I'm putting, the clay wants to go down the slope, but I'm putting a pile in its path, and the clay itself is quite strong. So the amount of lateral load that applies can be very big, and this was causing a lot of extra load onto the pile, and in fact causing the piles to either bend or fail because of the crust load. So liquefiable soil applying load is one thing, but if you have non-liquefiable crust on the top, that was even bigger problem for pile foundations. Does that make sense? So kinds of earthquake related problems. If there was, unless you make meters per second, if it's fine, you put a plastic sheet on the top, and you can use, this is what we mean by bending. You can see the other way, come lay distance to 0.75. This is empirical, so it's just trying to fit some field data and get this equation. T to the power of half and theta to the power of 0.3. Theta is the slope angle in degrees, and T, I believe, is the thickness of the clay layer, of the liquefiable layer. Okay, and all I did here is to plot slope angle versus lateral spreading for different thicknesses. So clearly the thicker, another way to predict the amount of lateral spread, these are Americans, okay? Bartlett and Youth. Youth is a fairly famous researcher, and I think he has a company now, anyhow. So they had collected 467 field cases of lateral spreads and came up with this equation. Whenever I see equations like this, my antenna go up and say, If you are putting so many logs in any equation, that basically means we don't understand the mechanics. If you plot on log axis, almost anything will become linear. You can plot earthquake strength versus stock market. As long as you make both axes log, you will get some correlation. That doesn't mean stock market exclusively varies with earthquake strength, does it? It's just a correlation. When you do statistics like this, I get a bit upset. That is because they're not showing any understanding of what's going on. I'm not saying this is as random as stock market variations, but you can see they picked up some reasonable things like the earthquake magnitude, moment magnitude. R is the uh, horizontal distance to nearest fault. S is the slope. This is clearly important. S is important. M probably is important. Why did I say probably? English is like a bit funny language like that. When I say probably, that means it is may or may not be true. Why am I saying that? You heard me plans, it should depend on earthquake strength. Go on.
For example, you show that earthquake was far away but still
Yes, that's one thing. The answer I'm looking for. Okay, so this fault distance also basically tells you what is the strength of the earthquake you can expect. If the fault distance to your actual site is very long, you expect the moment magnitude to be smaller. So they thought maybe we'll include that as well. And this is why they're not very clever. And then T15, this should be T sub 15, is the thickness of the saturated layer, liquefaction. So if I have 30, 40, 50% of fines content, then the liquefaction potential drops. The smaller the fines content, clean sands are the easiest to liquefy. And I think that was covered. Sub 15 is the average D50 grain size. I did one calculation, 100 or 500 millimeters. If this spread is going to be bigger than that, I will already mobilize evidence for that. Especially a historic. All these 467 case histories, you can predict ones, which is on the unsafe side. Okay. So this kind of plots are available, and again you can see these are done by American researchers. That's why these are all in horrible FPS units. What this is trying to do is to see the displacement, lateral displacement in inches plotted against the depth of the layer in inches, liquefiable layer in inches. And what it's trying to do, rightly or wrongly, is the slope is taken as 20 degrees. And what it is saying is when you shake it, what is the mode shape it will go to. So it can start somewhere like going upslope here to like this to downslope there. So cycle by cycle, I can accumulate movement towards the downslope. Okay, so if I have 10, 15 cycles, I can accumulate quite a lot of displacement cycle by cycle. And for the same data, I can also work out what is the shear stress on layers parallel to the slope. And these are plotted as shear stress in pounds per square inch, which is a favorite unit for the Americans. Pound is a force, obviously, but pound is also weight. So obviously what they mean here is LB force. pound force per square inch. We can sit down and convert all this into kPa quite easily. So 1 pound is 2.2 kilos, so it's about 22 newtons, and inch is 25.4 millimeters. Convert that into meters, and you can convert that into kPa with a factor. And again, you can see how the shear stress is more on when it's trying to go up slope and it drops off. As the soil liquefies, obviously the shear stress will become quite small, and that's why it's flowing. So this is quite right that at the end of the shaking, I got very little shear stress in the layers. Does that make sense? Yeah? Okay, anyhow, these are the plots one can get. But this is all to show that if I take an element here, soil element here, and track how it moves, it's going to oscillate and back and forth, and cycle by cycle, it will end up somewhere here. So it's not going to go like that. It will oscillate and it will go down. And in the video I've shown you yesterday, that was also what we observed, right? So that was on a 3-degree slope, I think I showed you. Right. Now let's do some proper mechanics. As I said, we are always focused in this course. It's you need to understand the mechanics of the problem to make predictions. In the absence of mechanics, you come up with empirical relationships. Some are good, some are bad, some are simple, some are a bit more complicated, but nonetheless, there's always an element of guesswork in that. It all depends on how good or bad your actual field data is. And even if AI takes over the world, for these kind of problems, it will struggle because the data we are giving it is quite bad. If data is bad, it can't come up somehow with the right mechanics. That we have to still do. And that's why I feel geotechnical, somebody was asking, is there future for geotechnical engineering in the era of AI? And I believe yes, because for good or bad, we actually don't understand soil all that well. If we don't understand, there's cat and hell's chance that AI can tell us what the soil is going to do. So first, humans should know what's going on, collect a lot of data, and then AI can help. But in the absence of that, there is very little chance that we will make progress with AI. So I wanted to kind of come back and teach you how to use this Newmarkian sliding block analysis. Newmark had the real honor. He was a professor of Berkeley, and the very first Rankin lecture he gave. Rankin lecture, have you heard about Rankin lecture? Hopefully, if you're in geotechnical engineering, you should have heard. Ranking lecture is about is the best honor anybody can get, you know. And the very first one he gave, and what he did in his ranking lecture is came up with this very simple mechanical sliding block. Okay, and I'm going to explain what that is. So it's particularly relevant for the problem we are trying to do here. This new board. So all he did was imagine I got a slope with some angle. Yeah, and you have a block. So that block has a mass m, right? even first year engineering student should know this. We will have a normal reaction to this, and what else will be there? I will ask some other student. Go on. What else should be there? So this is normal. There should be a one more force, right? So mg is that way, yeah, and I should have some r that way, right? Because the block wants to slide down, I'll get frictional resistance to oppose it. And mg cos beta will be one, mg sin beta will be the other, and we can work out the equilibrium of that, right? That is a block on a slope problem. A-level students should do that, or intermediate students should do that. Now, what he said is, let's imagine I'm going to shake this whole thing with some acceleration. So I'm going to shake this whole slope. What will the block do? Sorry? Okay, let's imagine I'm only going to apply a sinusoidal pulse. So this is my acceleration with time. Okay, that's what I'm applying at every point. So that's the acceleration pulse I'm giving it. So what will the block do? Okay, good. That is one answer. If I shake this strong, so I'll have the block which wants to slide down, but it's being held by their resistance force. If my downward acceleration times mass, if that force is bigger than r, then it will slide, right? In that first positive cycle. But in the negative cycle, the block is being accelerated up slope. If my pulse is big, it can also slide up slope, right? So what he basically said was, because these are all forces and I can divide the force by mass to get acceleration, what he said was, if I exceed a certain threshold acceleration, the block will slide, which is obvious to say. It's fairly basic mechanics. Going the upslope side, this is what is called threshold acceleration. Threshold for sliding. Wow. Yeah. When I want to slide upslope, this magnitude will be bit bigger, because now I need to overcome the r in the other direction and still go up, right? So if it is, say, here, then the block will not go up slope. It will only go down slope. But if it is maybe here, then it will go up as well. Okay? Right. So this threshold yield acceleration is what he was proposing. So he's done this for earth dams and how these slopes fail. If you go back, put into Google Newmark's Rankin lecture, it's all online, and he's done it to show earth dams can fail because of these type of accelerations. The upslope and downslope of an earth dam can fail because of this. At that time, it was quite important for people in Berkeley, because they had 3 or 4 San Fernando Dam and lots of other dams all around Berkeley. They had the what is now called Los Angeles Dam, but upper and lower San Fernando dams had some damage during earthquakes, and he thought this is an important topic to address in a big lecture like Ranking lecture. So that's what he's done. So If I now have more cycles, what will happen? So during this period, it will, because I'm only looking at one cycle, in that period from here to here, the block will slide. Yeah. But if I have more cycles, for every cycle, as soon as I cross the threshold acceleration, I'll accrue some more displacement down slope. Yeah. If I had a little bit of upward movement, then the block can go a little bit up. So it can do that, little bit that, more, little bit that, more that. Or it can do that, stop, that, stop, that, stop. That's what this mechanical model can predict. Anything you're not sure about, especially back of the class. Is this easy enough to do? Yeah? Right. So that is the fundamental concept that Newmark has come up with. And once I can get this concept in my head, then I can actually do some calculations. So if I integrate acceleration, what do I get? You get velocity. If I integrate velocity, what will I get? So what we can do is, can I rub this out? You got this, right? So I need a bit more space because I can only use this part, right? This part you can't see. Okay, we'll work around that. So that is my acceleration versus time. Yeah, let's, for sake of, let's say that's just 1 hertz pulse, and let's say that is about 0.4 g. Okay, and our threshold acceleration, let's set it at 0.3 g. And on the downslope, this will be also be 0.4 g. Let's say that this is 0.6 g. So if this is the case, I'll only get movement downslope and nothing upslope. Agreed? Okay. So what I want is to first, so I'm only interested in the acceleration above the threshold. In other words, this part. Yeah. So I'm going to plot the leftover bits here. Yes. Then you want to say, I'm going to integrate that to get my velocity. So that whole area, you know how to get area underneath a curve, right? Yes. So this will come out to be, so each bit you take as a little area, add that, you get a pulse like that. Yes. And same will be here, same will be here. And now I can do displacement versus time. One of the things you will see is, although acceleration is 0 there, the velocity actually will take some time to come to 0. The fact that acceleration has come to 0 means the body is not being subjected to acceleration, but it still has some velocity, right? So the displacement will accrue until velocity comes to 0. It basically takes, it's like stopping distance for a car. The stopping distance you calculate not based on acceleration or the braking force, but based on velocity coming to zero. It's the same thing here. So a lot of people who do numeric calculation actually don't understand this and make that mistake. Oh, my acceleration stops zero, therefore my body should stop. No, it will continue until velocity comes to zero. Right, so that now I can do this, then I can actually plot these displacements. So if I were to look at how this will accrue with time, it look like that. This will be displacement versus time accumulated plot. Does it make sense? So it will accrue displacements whenever it crosses the threshold acceleration. Yeah? Okay. So the block will slide and continue to accrue downslope displacement until the velocity falls to zero, and the sliding block can only slide upslope if my threshold acceleration uh, is reached on this side as well. So you can, if for a very steep slopes like 10 degrees, 6 degree, 10 degree slopes, the acceleration needed to go upslope will be quite high. But for 1 degree, 2 degree, 3 degree slopes, it may not be that much. Then you can say, right, it's not going to be 0.6 g, it will be say 0.35 g. And then you'll get bits here as well. Okay? And you must remember that is going upslope. So these, although you may get integrated values may be positive, but you must have the sense to say, no, my actual displacement is the other way. Yeah. So you will get something like a decrease here and then followed by down to zero. And then integrating that to displacement will give you something like that. Because I'm only plotting the whole, I'm always adding to the cumulative displacement. So you get something like 10, 15 millimeters. This is all at centrifuge scale, so you got to multiply that with n. But that demonstrates the principle of it. Right. There are more sophistications that can apply to Newmark. In fact, Bruce, Cutter, and myself were great fans of this. We are all Cambridge trained, so we are really into mechanics and estimating things based on mechanics. So he uses this. I recently used this to predict the, with a student, of course, flotation of a tunnel. Soil liquefies around the tunnel and it floats up. You can do FE stuff and so on. I think I showed you example of that before. But you can actually predict the upward movement simply by using Newmark's same concept of threshold acceleration. And it works beautifully. Because the mechanics is easy, it should work. Anyhow, if you, for liquefaction problems, we don't have this kind of sliding block alone. What we have is, when you are having this lateral spreading, it's really the excess pore pressure that is killing the strength. Once I got excess pore pressure, my effective stress comes down, which means my threshold acceleration to cause sliding is decreasing, right? So instead of being something like 0.3 g, that one will drop to say 0.05 g. Then I get huge amounts of spread, because now I'm integrating much bigger area, all this area will be included, right? So the threshold acceleration is coming down because of the excess pore water pressure. And that is what reduces the strength of the material or the sliding resistance capacity, if you like. Cutter and Balakrishnan they had even bigger, grander ideas of trying to link this. Yesterday, I mentioned that you can, the soil, when it fully liquefies, if you try to shear it, it will undergo dilation. And the dilation expresses itself as deliquefaction shock. We done that yesterday, right? So they tried to put that back into Newmark sliding block, where this line is not like that, but it can do. So say the threshold, I'll redraw it. You understand this, right? I'll clear this off. So what we are effectively saying is, okay, I got my 2 cycles. Say liquefaction made my threshold 0.05 G. Let's say that's 0.4 G, like before. But when I get this deliquefaction shock, this thing stays like that and jumps up. Does that make sense? So you can say the deliquefaction shock will create a temporary increase in your threshold acceleration, which means I can still handle this. It's not complicated. All I have to do is to say, I'm going to integrate the area between this bit. Yeah? Is that right? No, sorry. This bit. That's what we're looking at. So you can do the sine wave cut, integrate that, and subtract from this trapezoid. So it will reduce the amount of lateral spread. And that is quite right, because what the suction is doing is stopping the slope from moving, right? So it moves, stops, right? So if I have suddenly the pore pressure is going into negative and stopping the stiffening my soil, I expect smaller lateral spread to happen. So what started as a simple block on the slope has kind of, we are now putting higher and higher ragas and swaras and making it more complicated. However, the mechanics is still very simple. We can include some of these other features into this same idea of downslope movement. And this also explains why in the centrifuge tests and experiments we do, why we see the slope suddenly stops and then moves and stops and moves as well. And it's all linked to pore water pressure. In whole of soil mechanics, as I said yesterday, there are only one big thing you need to understand. The soil behavior is linked not only to the stress state it is in, but it is also dependent on its tendency to have volume changes. It's unique in that sense, unlike steel, concrete, any other carbon reinforced fiber, every other material, man-made material, granular materials like sands and even powders in chemical engineering, these have the unfortunate habit of trying to change their volume. And that's what makes it so exciting, because it's not easy. You can't map everything just based on stress. You have to worry about the third dimension, which is the change in void ratio, or in Cambridge we call it specific volume. It's the same thing. Okay, so Q, P dashed, and V is what the dimension, the 3D space you got to work in, and this is another classic example of that. Okay, last thing before we stop for tea. Oh, sorry. Some experimental evidence. This is, I think, all the way going back to my second PhD student. We could if you log the data quick enough, you can see these are very small times, right? This is in tens of milliseconds. You can see, so this is the earthquake we applied, more or less sinusoidal, and these are the pore pressures along the height. So deepest to shallowest. And we kind of zoomed them quite big, right? But what you can see is, you can look at this deliquefaction shock wave propagating. So this is not some myth that we created. You can actually see them in almost every centrifuge test we do. And that also tells you how, because it's a P wave, that is, it's a pressure wave, you can work out lots of other things. Like if I know P wave velocity, I can tell you degree of saturation and all kinds of other things. The Skempton's B parameter and other soil mechanics related stuff also falls out of this. But the biggest thing here is what Cutter and Balakrishnan said are the deliquefaction shocks. We can observe directly from the data. And this is Haskell's data I was showing yesterday, Jenny Haskell. Only one disappointment with this work is this New Zealand girl came on the Rutherford scholarship, worked very hard for 3.5 years, produced most wonderful experiments, wrote one geotechnic paper and some other conference papers, and then she got a lectureship back in Christchurch. She went there. 2 years later, she decided soil mechanics is not for her and went to Australia to study medicine. I said, what? I still don't know how far she got into her medical course. My daughter is still studying, and my daughter is a lot older than this girl. There's no end, right? After doing so much good work, why want to change? Anyhow, again, this is the evidence of propagation of the deliquefaction shocks in there. Weird people, New Zealanders. And you can look at the, I showed you this data yesterday as well. So it's basically, I'm showing now in the context of the suction cycles you're getting. Right. This is the bit I really want you to do. Okay. So either you take a photograph or you probably will get this slide through the website. What I want is, take a slope of 10 degrees. Okay. And let's imagine it is simply loose saturated sand, fully submerged. Okay. For the sand, let's say the peak friction angle is 35 degrees. So we are going to approximate the slope as a rigid block, and I would like you, the amplitude of the sine wave should be 0.6 G and the frequency of 1 Hertz. I'd like you to estimate the lateral spread, and you take the yield acceleration of about 0.2 G downslope and 0.4 G upslope. Okay? If nothing else, draw the sine wave, shade the area, count the squares, and that is also integration, right? So you can do it in any way, any number of ways. What I want for tomorrow is an answer. And if you had to make any assumptions, just explain. This is the critical point. Yeah. Instead of having 1 Hertz shake, if the frequency has gone up to 3 Hertz, yeah, redo the calculations for 3 Hertz. Again, still considering only one cycle. First one, you are taking one cycle. Second one also, you're taking one cycle. It's just the frequency is different. Okay. And I want you to tell me what you observed. What is the effect of frequency on the lateral spread? Just out of the cold, what do you think the effect of frequency will be.
Maybe rate of lateral spreading faster.
Maybe, but we are worried about magnitude, right?
But the rate is also matter.
Okay, do the calculation. Right. So, what we're going to do now is to look at the piles in laterally spreading soil. So, this morning we looked at the lateral spreading soils, why that happens, and came up with a way of estimating how big these can be. So, now what we want to do is to look at uh, what happens when piles are in place. So, I think this kind of was prepared on the assumption that you know already PY curves, but let me explain a little bit what PY curves are and then I'll explain this slide. Okay, suppose I have a pile in ground. Let's, for simplicity, assume it's rock socketed at the base and it's subjected to lateral load. So what we know, if it was just a cantilever, it's going to bend outwards, and we can even calculate how much the deflection is. If I know the load H and L is the length, then you would say the delta is going to be HL cube by 3EI, right? So that is easy. Now, obviously, piles are not sitting in air, they are sitting in soil. So as the pile wants to deflect like this, it will be opposed by the soil. So one way you can see how much resistance I get is by imagining my pile is made out of lots of elements and each of them has a horizontal spring. Okay? So when I am pushing like this, depending on how much deflection I get, I'll apply a spring force to oppose it. So if I know the force, I can divide that on the area of the element or projected area of the element, and that will be some form of pressure, right? So that will be the soil pressure generated to oppose the movement of my element. So far good. So each element will have some amount of pressure P, and that depends on the deflection, or if it is in air, we can work out how much the deflection is. If it is in the soil, we expect the deflection to be smaller. So what matters is the relative displacement between the pile and the soil. Okay? So that is called Y. So because we are using symbols P and Y, this is what the so-called PY analysis is. And people like Meyerhofen have done this for ages, for any laterally loaded piles in clays, sands, recent matlock and the rest of it. Now it's also very straightforward to imagine that, so that is say element 1 and this is element 2. So I can imagine that my element 2 is here. I got some more pressure distribution there. Yeah. and there is a torsional spring between the two. So this is what you would call the structural spring, which mimics the bending stiffness of the pile. So this K rotational spring is there because we took our pile and cut them into little elements, right? Obviously, the real pile is all one unit, so it'll have bending stiffness. So we can say, oh, okay, I'll take each of these as rigid, and my bending stiffness is giving me the, I'm mimicking that as the rotational stiffness of the spring. Now, as I go deeper and deeper, my pressure goes up, but my deflection, the y, which is the relative displacement, I'll write it down clearly. Y is the u pile minus u soil. So, so we should really call that a relative displacement. Yeah. So, what will happen as I go down towards the base? My relative deflection will get smaller and smaller, clearly, because it's trying to bend like a cantilever, right? But my pressure I get will be getting bigger and bigger. Understood? And the overall bending moment in the pile depends on the action between these two, which is big, which is small, and therefore we get different bending distributions. So this is the famous PY analysis, nothing more than that. Only thing here is we may get this deflection of the pile and deflection of the soil. If my soil is going for walking down the slope, then that's going to be a lot bigger than what the pile can do. So if my soil is coming and attacking the pile this way, it's not the fact that I'm applying a horizontal load, but I'm applying a big soil pressure that's causing my thing to bend. But it's exactly the same concept as this. This is originally developed for lateral load on piles, but what we are now saying is our load or force action or load action is not coming because of some external load, but it's coming because of the soil trying to move down slope. Okay, in the context of lateral spreading. So all we learned so far, we can put them all together, and you can say, if I plot the relative displacement on the x-axis and the reaction force or P or pressure on the y-axis, you can come up with some very simple relationships like, okay, at some point, the amount of pressure I can apply on the pile will be capped. Why is that? Why do you think that there should be a limit? So we have a PU ultimate, P ultimate. Why is there such a nice cutoff there? Can you think? Perfect. Yeah. So once you reach the passive capacity of the soil, it can't do any more. So there will always be some ultimate pressure. Perfect answer. So until that is reached, what we are saying here is, let's just say it's some linear increase, 0 till that point, and the slope of that is kh. Okay. So because that is force versus displacement, this is some kind of stiffness. Yeah. Okay. So this will be our relationship. Now what you can do is to say, okay, for the element number 1, I have that. Element 2, slightly bigger. So nth element here will have quite big force like that. So the PY curves we can change depending on depth. and then it gets quite realistic. So we're not saying one PY curve for all the elements. The PY curves themselves are scaled up depending on how deep you are. Okay? We're still not changing the stiffness. There are lots of things that are not quite right with it, but it is at least in UK we call it starter for 10. So for 10 points you can have a starter question. It's a game show thing, university challenge. Anyhow, so that is the basic idea of PY curves. Anybody not sure of what I said? Or is it clear? Okay. Now we can put this in the context of, we looked at different failure mechanisms, right? I've been showing for the last 2 days, and I'll show some more again, of how pile foundations can fail. So I'm plotting axial load on this axis, yeah, and on the x-axis I have increasing soil stiffness, and in the other direction I got increasing pile stiffness. So as I go from left to right, imagine soil stiffness is increasing, and if I go right to left, pile stiffness is increasing. For example, the piles are thicker and bigger and bigger diameter. Then I'll increase pile stiffness. Going right, I may be having stronger and stronger clay, for example, right? And in this direction, we are having axial load. So what we first did, and you worked out yesterday for coursework as well, is if my axial load is quite big, yeah, piles will buckle, right? Whether soil stiffness, pile stiffness, you will always find in this space, piles will buckle, right? And how big this is depends on, of course, the pile stiffness, but also the end conditions. Is it free-headed pile or fixed-headed, pinned, whatever the structural joint is, that will determine the magnitude, but certainly it will be in this space. And the most important thing is, these are all unstable states. Buckling is, as I said, keep banging on, is the instability that is the killer. That means you can't predict when it will fail. It will fail suddenly on you. So it is an unstable state. When the axial load is relatively small, if my soil stiffness is big and pile stiffness is small, what will happen? The soil is stiffer, pile is like thin guy, he'll get bent. So here I will encounter bending failure. Yeah. On the other hand, if my pile is very stiff and the soil is relatively weak, then I'll get more and more soil flow past the pile. So this is a neat framework to show. So all I really need to know is what is my axial load, what is my soil stiffness and pile stiffness, and I can then predict how my pile is actually going to behave, or how is it going to, how is it likely to fail. You like this? So everything we learned, we kind of are putting together into one unified state. Sorry. Yeah, please. No. Yeah, we will. This is the framework we are creating. Where exactly this falls, you need to populate that with data. Yeah, but this is. What I was trying to do is to say, okay, we saw all these individual cases, but there should be one overarching thing that holds it all together. In the end, I'll come and do this to say, especially for, we have done buckling bit, but for bending failures and soil flow, we will come and do this for single piles and pile groups. Okay? Which is what he's been waiting for last 2 days. He keeps telling me. Right. So this is about the easiest PY curve people have can imagine. However, there are slightly better ones. Some This is Tom O'Rourke and Go. Go is a professor, I believe, in NUS now. And back in '99, they came up with this shape. There are some good things and bad things about it. Let me explain. So here what you are doing is you are plotting the P on this axis and displacement on this axis, which is what our PY curve should be, right? Instead of plotting absolute values, what they have done is to normalize them, which is a good way of going about things. So the normalized force acting on the pile P divided by the undrained shear strength SU times the diameter. You should always make sure these are dimensionless, right? Let's just check that. P is kilonewtons over SUD. SU should be kilonewtons per meter squared, kPa, right? And D is the diameter. Also, I'll have, this is all done per meter depth of soil, right? Therefore, so this cancels, this is in meters, so that cancels, and therefore I'll end up with a non-dimensional group when I'm looking at force per meter depth. And similarly, this is also not, the displacement divided by the diameter of the pile will give me non-dimensional displacement. By doing this, what they could define the PY curve as, I mean, they have two, rough pile surface being rough or pile surface being smooth. So they proposed two curves, but you can define these with only four parameters. Slope of this line, KL, location of the peak, slope of that, and residual value here. So only four parameters are needed to define this. And this is kind of quite highly quoted paper, and it so happens that they basically over-constrained this problem. You actually should not apply four restrictions where there are only three variables. So that is called over-constraining the problem. If you do that, you can almost fit anything, any data to this, and it will work. This was pointed out to Tom when he was on sabbatical to us, and ever since then he respects us a lot more because we pointed out what is obviously a flaw in the model. Anyhow, but that is the, again, a framework for this. One of the, this is kind of better than this because this is assuming that I'll reach some PU and stay constant, right? What this is telling us is, yes, I'll reach some peak value at fairly small displacements, right? Then it will soften. So this is a negative slope, right? And you will reach some residual value. And this is quite good observation that when the slopes start to move for the PY curves, initial stiffness can be big. But as they continue to move, it will reduce the force because of lateral spreading, liquefaction, and the rest of it. And then you reach some residual value at the end. This, they have this parameter SU, P, and residual value, right? SU minimum. They proposed this for the, to work out how much they are. So the upper limit of SU they say simply take that as 0.17 of the mean confining stress. The lower limit of that is 3.4% of the initial stress, initial effective stress, mean confining stress. Okay? So they also say it only takes 0.02% strain to drop from this peak value to residual value. Okay? So this is all like a nice recipe to work out the how the pressure on the pile can be calculated, or how the lateral pressure can be calculated. There is another issue which comes from a different source. The undrained shear strength of clays, we are mostly worried about clay because what I said in the morning, because of the clay crust on the top. That's where we will come back to. This, so clay will have undrained shear strength, which we all know or can work out. Simple UCS test should tell us that. But what happens when you subject the clay to cycles? It will soften. Okay, if you apply an earthquake loading to a nice clay bed, it will soften with cycles. And we have now got experimental evidence. Tejesh and other people have done this with clays, and there is enough data on that. Back in 95, this is a very popular paper where Liu and Dobry came up with this degradation of the strength. Suppose I have a multiplier coefficient for my strength of Cu. Okay, so when no cyclic loading is applied, it will be say 1. Yeah, if I cycle and mobilize a lot of pore pressure, then it will drop from all the way from 1 to almost 0.1, a factor of 10 drop. Typically, clays don't produce that kind of pore pressure. You'll get something like maybe 20, 30, 40 kPa, right? So it will be maybe 80% drop or 70% drop. Whereas sands obviously will liquefy, therefore they'll go all the way to 0. But this observation, this data from Liu and Dobry is very widely used and quoted, and it's considered to be pretty good. Okay? Okay. So far, these are all the things we need to know about piles and laterally spreading soils, and how we can adapt the traditional PY analysis to get the to fit into those models, right? Go and Rourke or somebody like that, that kind of model. What obviously I felt when we started this journey was that, yeah, but this is all based on cyclic triaxial tests and everything else other than actually doing proper physical modeling. So the first thing we did was to take a single pile and look at it using laterally spreading soils. So this work was done by my second PhD student and now my colleague, Professor Stuart Haig, and it was a real excellent piece of research. So what we wanted to do was obviously do the centrifuge test, but really we wanted to get the next to the pile, what are the stress paths the soil is going to follow. So near pile stress paths, We tried to do this using miniature pressure cells. Nobody believes earth pressure cells, or you should not put all your money onto earth pressure cells. Earth pressure measurement is one of the hardest things to do in soil mechanics. So we also had bending moment strain gauges on the piles to measure bending moment and the pile loads. Then what the prize at that point was that we can compare all this with design code. And the design code was being proposed by Japanese railway authority, I think JRA it's called, and they came up with a design code, and we wanted to show that was rubbish, as you'd expect. And then I'll provide some conclusions on the single pile. So the experiment was dead simple. Just a single pile, no vertical load. The pile went all the way through the slope into dense sand. Yeah. But if I look at this on the plan view, we had actually two piles, one behind the other, because the width of the box is big enough. And this was another favorite of mine, where you can have in practice circular piles, but you can also have square piles. Some bridges and all will have square piles too. My idea was that if the soil is trying to flow down the slope, surely the shape of the pile should make a difference. Because if it is circular pile, I'll get nice continuous flow lines. If it is square pile, you get discontinuity of flow around it. It's same as any fluid mechanics problem. Okay. So this was the aim. So we had pore pressure transducers very close to the pile, and also some earth pressure cells. So the input was sinusoidal. This is the old SAM actuator, and we applied something quite large number of cycles with about 1 meter per second squared will give you something like 0.1 G earthquake, right? Yeah, 9.8 meters is 1 G, so this is about 0.1 G shaking, and 1 hertz at prototype scale. So the genius of Stuart Haig was that I thought I had to spend a lot of money making square piles and circular piles and so on, and keep changing the stiffness, because one of the parameters is the stiffness. What he did was to say, no, 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 we will use aluminum blades which are actually strain gauged to measure the bending. And then he made the rest of the pile with dense foam. So he could easily change the pile dimension, but the stiffness will be the same, because most of the stiffness is coming from the aluminum. The foam ain't going to do anything to the stiffness, but the foam will dictate how much load the pile will attract, because if I have a big diameter foam, I'll get more load. If I have small diameter, I'll get less load. So this is a very flexible pile design he came up with. Okay, so let's first look at the pore pressures on either side of the pile. So we got upslope at one depth and this 40 millimeter depth and 70 millimeter depth, and also at the same location on the downslope as well of the pile. So you can see that if these two are at the same depth, upslope and downslope, and these two are the same 3.5 meter depth, prototype scale, upslope and downslope. Firstly, although they're next to each other on either side of the pile, the response is very different, right? That much there should not be any controversy, because you can see that's gone up and doing that, this has gone up, and these producing really big suctions here. Now, if I have an object like this, and I'm measuring pressure here and on the other side, I can now take the difference between the two, yeah, and multiply with the area to get the force, right? So we could work out what is the these pore pressures, because they are different, how much force they are applying on the pile. This is getting less of an issue as you go deeper into the slope. These two look a lot more similar than these two, right? So the pile is trying to bend, and here at this shallow depth, they're very different, whereas at a deeper level, they're similar. And the deeper we go, the more similar they will get. Agree? That's what the data is showing us. So we also did tests with flexible piles, because we can change the blades, uh, and also relatively rigid piles. Again, comparing upslope and downslope. So these are the upslope ones and these are the downslope ones, flexible and rigid. So when my pile is rigid, I'm not getting upslope as much oscillations in my pore water pressure. When it's flexible, I'm getting a lot bigger cycles. And that makes sense. If the pile is flexible, it can do that a lot, and upslope, I will pick that up. If my pile is rigid, then it won't let the soil oscillate so easily, so I'm not getting those oscillations. So immediately you can see what the effect of a rigid pile versus flexible pile is. Downslope, whether the pile is flexible or rigid, it's not making that much of a difference, right? So I'm getting big suctions here and also big suctions here. Does that make sense? Why do you think that is? You're not going to sit in my lecture and just drift off. I will keep coming back and asking questions.
Flow mechanics is doing great. So the pressure forward more active.
There, the pile is so small, the overburden stress on both sides is very similar. Big point is maybe that's what you're trying to say. Probably yes, probably not. I'm not sure. Basically, say the pile is here and the soil is flowing this way. When the soil is upslope, it will be, it's moving towards the pile. So if the pile is rigid, it is constrained, right? The soil on the other side, even if the pile is rigid, it's not being constrained going down slope. So this bit is always free to go where he wants to go, right? So this is why even for rigid pile, down slope, I'm getting all the oscillations. Okay? Upslope obviously will be similar, but downslope also, even if the pile is rigid, it will go. Yeah. So that is the explanation reason why these are measured like that. Now I can now even work out how much the hydrodynamic force I'm going to get, which will be the difference between the pore pressures at different elevations, and you can see how big these are. Again, these are calculations. Do you know why that is not? Yeah, okay. So flexible pile and different depths. These are basically plotted as the difference between the two pore pressures on either side. This is the direct force the pile will feel. So these are shown as pressures, but you need to convert that into, using the area, you need to convert that into forces if you want. So that is for flexible pile and this is for rigid pile. Okay, so far so good. But now we have the earth pressures. We can also look at these contact stresses, and you can see upslope and downslope, one depth and deeper levels. So again, you can see how big these earth pressures are, or contact stresses are coming. This is going from naught to about 40 kilopascals. This one downslope, obviously, the soil is going away from the pile. So these are a lot smaller, right? And again, at deeper depth, this is even bigger than, this is almost 50 kilopascals of pressure. Here, almost just about 20. So upslope, I'll get big earth pressure coming onto my pile. Downslope, it is disappearing. Although the contact pressure cells are not the best, at least they are doing the right kind of thing. Actually, they work better in this kind of earthquake problems because all the arching effects and all get destroyed when you start shaking the soil. So it's not as bad as in some of the static earth pressures you would measure. And this is where we feel proud of ourselves. Now we have the vertical stress and the overburden stress and the horizontal stress. We can plot the stress paths, right? Because we know the pore water pressure, you can plot the active earth pressure line and passive earth pressure line and see where my stress path is falling, upslope and downslope. So at 2 meter depth, so upslope the soil is trying to do something, starts here and ends up there. So clearly it's very close to being fully mobilizing its passive earth pressure capacity, fully mobilizing the passive earth pressure. Downslope, no, it's kind of oscillating between active and passive because that bit of soil element downslope is free to go where he wants to go. So no point generating more earth pressure than it has to. That's why it can oscillate between Ka and Kp quite nicely, almost equally. Okay? The deeper I go, the more cycling I do and more towards Kp I am, upslope. Downslope, more towards Ka I am. So once you have good experimental data, you can get quite a lot of information on the soil stress state as well. And now you do this, if you ask your Plaxis or Abacus or whatever, plot me the stress path, then you know whether your code is working or not. If you have laterally spreading soil in Plaxis and say, next to my pile, give me the stress path, now you know where they should be. Upslope, it should be close to Kp. Downslope, it should be almost equal between Ka and Kp. If that pattern is not there, then there's something funky going on in your code. Because that's what you need. With FE models, you will always get some result, right? But whether the result is any good or not, you need to be able to judge. And these are ways in which we, because we have experimental data, we know this, we put in all the thinking already and it is there. So you can take advantage of that. Okay? So that was for rigid piles, and these are for more flexible piles. The more flexible I am, oh, these are all for 3.5 meter depth flexible pile uh, on the top and rigid piles at the bottom. And again, you can see, so this we have already seen. This one goes even further up the KP line. And downslope, you are always getting these loops. And I already explained that. Now, from a design point of view, like most structural engineers, they don't really care for pore pressures, earth pressures. All that is for geotech people to worry about. What they want is bending moment. Will my pile take this or will it fail? So we obviously want to measure the bending moment. I've shown you the gauges, and these are at different depths along the pile: 1.25 meters, 2.5, 3.75. And as I said before, we wanted to see whether it makes a difference to have circular and square pile. Because it's all made out of blue foam, he could cut it either as square or circular as he wanted. And turns out my initial hunch was not as hot as I thought it would be. So at shallow, I mean, if I shown you this and said that is for circular pile and this is for square pile, you'd say, well, if I change the titles the other way, you probably can't tell the difference. So from a bending moment point of view, in other words, the load that the pile is attracting was pretty similar. Yeah. So you would say not much difference. So we can't really optimize on the shape. But where it was, okay, there's a bit I need to explain here. What we observed, I don't think I made the slide for it. I'm going to draw these in plan view. Say that is the plan view, that is my circular pile. What we observed was, say the flow is of soil is like that. Yeah. And for square pile, what we saw was it was going a lot more like that. So although the bending moment is the same, the zone of influence of a square pile was much wider than the circular pile. At that point, my thought was, really this is going to make a big difference when you have multiple piles, right? If I have a lot of piles, then each will, say, depending on pile spacing, this zone will overlap with the pile in the next direction, and therefore the soil will have to make even more deviation and it can't flow in between the piles. This was back in 2001 when the student did his PhD. So I said, maybe we should put multiple piles. And he kind of threw his arms up and said, no, I've done enough work. I can't keep doing more tests with more piles. Maybe we'll do that later. Now it's 2025, right? This almost 25 years later. Now this thing has come up again, and he has a PhD student himself who's looking at many piles. This is a big problem in China. What they are trying to do is to create diaphragm walls by having contiguous piles. So if you have contiguous piles, it costs you a lot of money because every pile is next to another pile, next to another pile, like that. That's how you create these walls. So they had the brilliant idea that maybe we can avoid some of the in-between piles and the clay can't squeeze past, which is exactly the same problem as this. So we are, after all this time, we are now looking at the same problem again for diaphragm walls. So anyhow, so the bending moment is the same, but the flow pattern is different. What that means is, although I attract the same load per pile, the where the load is coming from, the soil is different. So this depends on a lot more volume of soil applying smaller pressure, whereas this one is very focused but with higher pressure. So the sum is the same, but the volume is different. Okay, that's the extra bit I wanted to say there. Now, as I said, these people, Japanese Rail Authority, came up with this code, and they made a blanket statement. This is always bad in any code, particularly to do with earthquakes. They said for any non-liquefied crust on the surface, the where we started this morning, you can take 30% of total vertical stress and apply that as the lateral load onto the pile. Sorry, no, my fault. For they're not that stupid. Sorry, the lateral pile loading. So I'll draw the picture from the morning. My apologies. So we got. So this is the sand, liquefied, and this is the clay. So what they're saying is, if I go to pile, going like that, here apply Kp. Use Kp to work out the horizontal pressure. Fair enough, because that is clay. For all this, typically this is 1 to 2 meters, and these are 10 to 15 meters, especially in Japan, right? So they're saying take 30% of the overburden stress of sigma V, not dashed, and apply that as the lateral pressure. Where they got this 30%, nobody knows. It's just a number they picked. So we thought, hang on, we've done all these tests. Surely we have the data to see whether this is conservative or unconservative. And here you go. These are the bending moment with the depth. Yeah. So the JRA production, we basically use this rule to calculate our the bending moment in the pile, and that is what JRA gives you. From our own experimental observations, this is the bending moment variation with depth. Yes, the square and circular piles are pretty similar. As I said before, they're not that different. But if I compare this to this, I'm underestimating my bending moment by a factor of, say, at a depth of 4 meters, this is maybe 70, and that is more like 160. So a factor of 2, right? What is the normal factor of safety people use on pile design? About 2. So this is why a lot of these piles are failing. Okay? So when you do tests like this, you can then go and challenge any existing wisdom. I'm not blaming JRA fully, because they are the ones with the problem. Earthquakes are happening every time. They have to have some rule which engineers can use to design. But in their haste, they didn't consider a lot of these very carefully. Although they say use Kp, because the thickness of the non-liquefied layer on the top is quite small, even if you add that, it comes to be a fairly small value. Yes, the pressure is more, but it's only on thin layer, whereas most of your pile is in the liquefied soil layer, right? So this is bending moment. This is the net horizontal stress. Again, that is quite small compared to where we were making our own measurements from the unreliable contact earth pressure cells. But at least you can get a similar order of difference in magnitude between what they are saying you should use for design and what we were measuring. So we wrote back to JRA saying this is our observation, and they never came back. When it is convenient, they don't understand English. Anyhow, so in summary of single pile, what have we learned? We are very sure that soil dilation close to the pile causes this transient loading. That's why you're getting those suctions and differential earth pressure, pore pressures. And as liquefied soil wants to go past the pile, it gets sheared, and if it gets sheared, it tries to create suction, and that means it gets stronger, therefore it can apply bigger load. This is the underlying mechanism that is causing us all the trouble with this problem. Okay? So, more flexible the pile is, less load it attracts. That's fairly obvious to say. You know, in engineering, the basic principle is that of unstoppable force and immovable object. Have you heard of that? No. Okay, this is like a common thing in physics. If I have an object, yeah, on which I can apply infinite force, right? Normally, if I increase the force, the object will move, right? But if the object is immovable and I can apply infinite force, then I can keep applying bigger and bigger force, and because it can't move. So that is not possible in physics. At some point, the body will move, right? So if the body is able to move, it will attract lesser force. And the same thing applies here. This is the pile flexibility reduces the load it attracts. Square and circular piles, to my great disappointment, attracted the same loading and created the same bending moment. However, what we observed was the zone over which it mobilizes is different, especially at the peak load. And the JRA code underpredicts both the peak bending moment and peak horizontal earth pressures by quite a lot. Okay? Residual values are comparable. Once the earthquake finishes, what they get is pretty similar to what we got was similar to JRA's predictions. But the whole point is your pile has already failed during the earthquake. So whether you got the residual value or not doesn't really matter. This is just to save. You must always give some room to save their faces, otherwise they feel bad. So you got residual values, okay. Your peak values are a factor of 2 off, so your pile has died during the earthquake, by the way. Okay, now I need to go into pile groups in laterally spreading soil. Do you want me to start this now, or do you want to go for lunch and come back? It's up to you. You want to have lunch and come back? Sure. Okay, sir? Okay, we'll start again at 2. Perfect. Hmm? Yeah. Pre-lunch lecture was to deal with single pile. Yeah. But as I was saying yesterday, very rarely single piles are used in practice. It's always going to be pile groups. Now, pile groups sitting in laterally spreading soil are a real concern. So, one of the mechanisms we envisaged, as I said before, is to do with this four hinge mechanism. If it's a 2 by 2 pile group, there are two other piles behind it, but you can say that is a kinematically admissible mechanism, right? So the piles deform in the liquefied soil and the whole thing spreads that way. But when you have no, this is like a idealized case where I got some bedrock into which I can rock socket the piles. Now, most cases, most general cases, foundations are placed into some, you go through surface layer and you go through liquefiable layer, and clearly this is loose sand, so you're not going to terminate your piles into loose sand. You'll find either dense sand or stiff clay below it, and you drive the pile into, and the pile tips in there, right? Now, if this is the case, what will be the failure mechanism, right? So, although these are easy to calculate, these are not the most general case. So working out the buckling load for this you have already done. So this is easy calculation to do. So first thing when you're designing piles, you want to make sure is do the buckling calculation. Make sure that your buckling load is maybe 7, 8 times larger than the actual load you're going to apply, so that the piles will not buckle. This is the same approach a structural engineer will take when they're designing columns, right? When the columns are being designed, they'll check for the buckling load. If it is coming anything like 2 times or 3 times of the load that column is going to carry, they'll get scared. So what they'll do is start designing some struts, horizontal struts to support the columns. So quick check, make sure that doesn't happen. Then you will have this kind of situation where you have non-liquefiable layer on the top, liquefiable sand and dense sand. So what is the mechanism we expect here? We expect that the pile will now translate a bit horizontally, but also settle a bit. So the moment I can get some settlement into dense sand, then my tendency to buckle will go away, because I'm no longer imposing zero displacement at the pile tip. So these kind of piles very rarely will buckle, because the buckling load will be a lot higher, and if you are applying anything like that, it's easy for the pile to settle. That doesn't mean the pile won't have bending. The pile will still, it's settled, but also it is trying to bend a bit. So you're still in the bending regime I've shown you in the morning. Okay, so you get some settlement and some lateral movement and also some bending, because this obviously doesn't move laterally as much as this can. This one is going for a ride with this layer. This is sitting on liquefiable layer. We talked about formation of water film here, which means this is trying to go a lot. But the tip of the pile doesn't like traveling that much in dense sand, because if you try to shear dense sand, it will oppose that even more strongly, because it can dilate even strongly, more strongly than the liquefied soil can. So this is a plausible and more realistic mechanism. Okay. And this is where we can do some fairly simple calculations. So, say you are in level ground to start with, you can say the non-liquefiable crust is going to apply the full passive pressure. So, for clayey soils, you know how to work out Kp. Yeah, you should have done that as maybe third year geotech or fourth year undergraduate course. How do you work out passive earth pressure for just clay? Yeah, if it is sand, it will be 1 plus sine phi by 1 minus sine phi. If it is clay, what should it be? Anybody remembers? 2 Cu? Okay, okay. So that we can very easily calculate. These layers are always going to be fairly of limited thickness, maybe 1 to 2 meters. So although I am applying passive pressure, that triangle is going to be fairly small. Okay. In the simplest of cases, we can say the liquefiable soil, as it is trying to go towards the pile, is applying some kind of uniform pressure. This is obviously simplification. In reality, it will be some kind of a trapezium, right? Let's say, let's keep it simple. It's already liquefied. It has to dilate as it goes past the soil, goes past the pile, and let's say that for simple case, we'll say take that as uniform. And at the base of this, between the bearing layer and here, you can apply some torsional spring with some rotational stiffness be applied, which is Kr. Okay? Right. So now I want to draw the equilibrium of this pile. So what are the forces acting on it? The forces that are acting horizontally are the liquefied soil pressure. You can use Go and O'Rourke, Tom O'Rourke and Go approximation, work out what this is, apply that as a uniform pressure and say, and that times the outer diameter of the pile. Because the pile is going to be like this, the soil is going to come, so the projected width is d naught, right? So that will be, so I am multiplying with the d naught, then this is the pressure distribution. At the base, I got some shear, at the interface, I got some shear force Fa, a bending moment of Ma. So at the top, I got another shear Fb and a resisting moment Mb. So this is like now a beam on which I got uniform pressure on one side and I got the shear forces and the resisting moments on the other side. One thing that we have added here, and this is the new bit, is the actual load the pile is carrying. So we should not forget this, because these piles which are on slopes are not just there for fun. They are carrying some actual axial load. Why is this important? The moment this pile is going to try and bend outwards, I'm going to get that P times delta as an extra moment. So every element on this pile has to work to resist that P delta effect. Okay? So this is the equilibrium of forces. And the thing we can play with is the EI of the pile, because that's what it has. It has flexural stiffness. E Young's modulus, I is the second moment of area. Do they still call I as moment of inertia? Second moment of area is what it should be called. But when I was growing up, we always called that moment of inertia. Because it has no density term, it's not mass moment of, there will be some 2 by 2 pile group, so there will be other piles here. So because of the frame action, structurally, these piles, one will go into more compression, the other one will go into tension. That has to happen. That is just structural mechanics, right? So, in fact, the settlement in the pile group, if I go back, it may be that one of them will settle a bit more than the other. Okay? So, I can write these equations here to, first of all, the moment equilibrium and then the force equilibrium. That's all these are. F crust, I can say what is the stiffness of the crust layer, and then how much does the crust wants to move minus how much the pile is allowed to move. So that is the relative displacement between how the crust movement and the pile movement, pile cap movement. So that is how much force due to crust will come on to my pile cap. Okay, so these are fairly straightforward to write. So FA simply is the difference between the moments plus, if I take that as uniform pressure, PLD L square by 2 because it's a distributed load, minus P delta over the length of the pile in the liquefiable layer. So that's what we are calling LEQ. Okay, FB will be minus FA because it's opposing that movement, plus so this is basically, this is the moment equilibrium, this is the force equilibrium, horizontal force equilibrium. So there you go. So this kind of thing we can do very easily, right? So even if I assume some kind of a trapezoidal distribution here, I can still adjust those equations to account for that. We know how to do forces acting on beams is something we learnt many years ago, and they're very easy to apply. Okay. For moment equilibrium, you can also simplify those equations by using mu, which is nothing but square root of axial load over EI. So this is almost telling us what the load applied force P is, or load P is, relative to its flexural stiffness. Okay, and basically if you plug these in, the mu's, it will become fairly obvious. It's going to come down to the P delta effect there as well. Then you can do this kind of limit equilibrium analysis where I'm plotting along the x-axis some mu. Okay, if my mu L is very big, then F delta will become small and FPL will increase. So that bit we've done assuming the pile is completely going to remain elastic, because we are simply applying the forces and it's all elastic analysis, right? However, we are also interested in when the pile is actually going to fail. So what you want to think about is, what is the delta I'm applying to the pile compared to the force from the crust. So the limit for this is the passive limit that you are mentioning. So that is, the soil has to yield beyond that point. But many times the structural failure, so it will behave linearly up to there, and then it reaches some plastic MP value for the pile, and that is what causes structural failure. Now this point here is when the first yield occurs. So in elastoplastic analysis like this, you simplify the whole problem by saying, well, I got the elastic bit and I got the plastic bit. You do not take the increase from first yield to peak and then softening. For steel piles, that can happen. But you ignore that bit and say that is the factor of safety in my back pocket. So that is normal plasticity assumption. Now, what you have here is how much is the crust wants to move, which we calculated in the first lecture. So this is how much the crust wants to slide down due to lateral spreading. Yeah. And versus how much the pile wants to move. We said the relative displacement is the important bit, right? Now, one thing you want to make sure is if I draw a line 1 in 1 with a slope of 1, that means the pile movement and the crust movement are exactly the same, right? So, if that is the case, the pile should not see any force. Displacement is more than the pile displacement, right? That's when trouble begins. Because that's when the soil wants to move more, the pile doesn't want to move as much. Therefore, the soil will collide with the pile and therefore will create the extra earth pressure. So, it's a simple way of looking at that. By looking at how much is the elastic deflection I get for the pile compared to how much crust displacement I can estimate using something like Newmark sliding block. Okay. If this is the case, we are designing for the pile to fail way before the soil will fail, right? But imagine that my soil is, the crust soil is weak. It's not very stiff, non-liquefiable layer. It's fairly soft clay. Then the structural failure will happen much higher compared to the soil yield. So the pile will stay where it wants to, and the soil is going to try and flow past around it, and therefore will apply the full passive pressure, whatever it can. So again, we'll take this linear bit, and it can't go past this because the soil has failed. So this is the limit of the what the soil can apply as a force, right? So you stop there and you go down here. Now what you have is this crust displacement here, pile displacement here. If I come down here, this is the 1 in 1 line, and basically I'll come up to here and my crust displacement increases while the pile displacement doesn't change anymore. Does that make sense? Because the soil has failed, therefore it can flow. So the crust will continue to deform or go down the slope, but it is just going around the pile. And the pile says, that's okay for me, I'll just sit there. So you won't get any increase in delta, the pile tip displacement anymore, pile top displacement anymore, while the crust displacement increases. Okay. Now what we want is, all this looks great, but based on some, as I said, all we have done there is mechanics again. But those mechanics are underpinned by expertise, maybe. Circular section D. So MP is going to be ZP times yield stress. And for circular section, ZP is pi by 32, I think, D. Is it 4 or 3? 3. Anyhow, any structural data book will give you that. Or you can Google it. Oh, radius, right? Yeah. I'm good. Yeah, whatever the equation, you can find the right one. So what? Yeah. Anyhow, so radius of gyration also comes into it. Yeah. Okay, so that we know, and for this it was calculated at about 180 kilonewton meters for the experimental pile. Yeah, and then we obviously we had a aluminum pile, calculated the ZP for that, and the yield stress for and then converted that into prototype scale using the scaling laws we learned yesterday. So that is the limit. Now we are looking at slowly increasing my pile displacement here. So what is happening to MA and what is happening to MB? Because these are something we can measure in the experiment, right? So as the delta increases, it was going up, MA is going up there, MB initially goes up to there, and then MB reached its limit while this tries to increase. Obviously, it can't go past there, yeah, because that is you reach the moment capacity. Therefore, you would expect the failure to happen somewhere there, where at the top of the pile. Understood? And that will happen at a displacement of about 0.3 meters. So if my lateral spread is going to be 0.3 meters or more, my pile is dead. Agreed? So if I were to look at the width depth, the bending moment distribution, for different amounts of deflection, 0.1, 0.2, 0.3, you can plot this. Because the pile cap is so rigid, there's no change in, so that's pretty much zero bending moment there. But it will have, the pile will have some moment, which is my MA being applied. And that obviously is increasing with deflections. At the base, where we marked MB, you can also see these are increasing as we increase the deflection, right? So you can then mark where my MP value is and see who's coming closest. So that will tell you whether the pile will have a plastic hinge forming at the base or at the top. So accordingly, you can even adjust your pile reinforcement to make sure that doesn't happen. Okay? So, but that is structural detail. But this is the bit structural engineers don't understand. This is what we got to tell them. When they come and ask you for spring stiffness and stupid things like that, you got to show them this and say, no, it's not like that. It's like this. You go and design so that at the top of the pile, even with 0.3 meters, I get at least a moment capacity greater than 100. And at the bottom, it should be maybe close to 150. And then they can design. Because if you tell them sensible things, structural engineers can handle that. If you say, well, it's all complicated, then they'll run away and never come to see us. So that is for single pile. Yeah? For pile group, what's going to happen? Similar situation where we are now getting MA and MB all will line up because they're all like, you got the frame action. So MA and MB will be the same. Ultimate is drawn here, which means I can allow up to about let's say 0.35 meters of deflection. By that point, I will reach my full plastic moment capacity. Yeah? So we'll do the same thing, different levels of deflection of the pile cap, 0.1, 0.2, 0.3, and you can see it goes first for 0.1 it's okay, 0.2 maybe okay, 0.3 it died. Yeah, and it dies because MA and MB are both the same because of the frame action. Both will form hinges. So the pile will dive by forming a hinge on the top and a hinge at the bottom, like what I've shown in the very first slide. Okay? Now we got the proof, and we can also tell how much deflection it can tolerate by the time it gets. This is all pure structural analysis. Yeah, we haven't done any magic with this. This is how much structurally I can deflect to get the failure or plastic moment, hinge formation. Whether there's a bit of an esoteric question where you can say, if the plastic hinge forms within the pile, would you call that failure or not? Now that is way beyond where we are now for piles. Normally, when you're doing pile design, if they formed plastic hinges, you'll say tata bye bye, the pile has had its day, right? However, more recent British standards and probably Eurocode as well, they are allowing plastic hinge formation in retaining walls, steel retaining walls, because even suppose you know what retaining wall is. I got soil this side, excavation this side. Even if I form plastic hinge at this level, it will deflect. But to deflect this, I need to spend energy in rotating the hinge, right? So I still have some more extra capacity. So what they want to say is that, can you utilize that extra plastic capacity as well by allowing some more deflection? Okay, as long as the wall doesn't collapse, you're okay, right? If I got more tip deflection at the top of the retaining wall, maybe it's okay. So that's happening in retaining walls. It hasn't come as far as piles yet. The problem is retaining walls. If the top deflects, you probably don't care that much. Okay, yeah, instead of 0.05 meters, it deflected to 0.1 meters. Nobody is going to die, the wall is not going to collapse, it's all okay. Problem with piles is, once you reach the plastic hinge, that means I undergone already 0.3 meters for this particular case, right? Then the P delta effects start to dominate, because I still have to carry the axial load. So the worry is that although I have this plastic moment capacity, the more deflection I give, the worse it gets, the more the P delta moment will become. So therefore, that hasn't percolated to these, and nobody has done enough research to say, after the plastic hinge has formed, how much load, how long before I will completely collapse the pile. So there are reasons for it. Sorry. Anything you're not sure about so far? This is a little bit heavy duty stuff. That's why I thought we'll have lunch and come back and go through it. And you've been asking for last 2 days, when are you going to teach file groups? So there's a good reason why I had to cover everything else before I got here. Yeah? Okay. Now, as was the theme, it's one thing to do all that with no experimental evidence, but that's not my game. My game is to say, right, that is the theory or the framework we have. How much validity it has can only come from some experimental evidence. So this Jonathan Knappett, who is a professor now in Oxford, I must say, he's done very well. He done these experiments where we have piles, yeah, in going through liquefiable layer. We had some kaolin clay, which is pre-consolidated to have a given undrained shear strength. So the clay is homemade, or we make it ourselves. So we know exactly what strength it is. Then we had a liquefiable layer, relative density of about 35. Have some water here somewhere. So thank you. So we know when we shake, that will definitely liquefy, and below that we have dense and relative density of 85%. And to do this accurately, somebody was asking yesterday, how are you sure that you get this relative density? We built a machine which can pour the sand to the density you want. So you tell the program how much the speed at which it pours, and you will get the right relative density. So to do one piece of research, you need lots of kit, and we also needed the laminar box. So a lot of things have to fall into place. Anyhow, here we are, geotechnical engineering. So feel free to have a look. And lots of instrumentation as well. So one of the things, I input acceleration, one was 0.2, the other one was 0.26, but as I said, these have very little influence on the liquefaction. Once it's above 0.1 g, it will liquefy the soil. So that's not a big deal. 2.25 meters and 3 meters. Okay, not of the pile, sorry, the slope. But the loads are, one is 345 kilonewtons, the other one is almost, it was 1155 kilonewtons, which is a factor of 3 times more, roughly. So we are deliberately going past what normally people would use as a factor of safety in pile design. Pile design, normally you apply a factor of safety between 2 and 2.5. We said no, we will apply a load which is way above that. And what we are interested in here is the lateral load and deflection response. So this is the lateral load that is being generated, okay, and that is the deflection. So all these squiggly lines are the actual, so we are monitoring how much the pile is horizontally deflecting and also what is the load on it. So you're plotting one against the other. So they, of course, because there are 4 piles. And delta is the how much the deflection is happening. So at the beginning, horizontal load is 0 and deflection is 0. Again, classical clay behavior. So initially, it thinks it is quite stiff, and if you apply enough cycles, it softens. Please tell John. Next time you come into contact, say, no, I have seen. So no strain rate effects and all that jazz. We are applying at like good 1 hertz frequency here. So peak and then it softens. Yeah. What Jonathan also did is to look at the residual going positive and also negative, right? Upslope, downslope. Sorry, downslope, upslope. But what is the net effect of all this is also marked here, what he calls residual, or there's a so this is when we increased that by a factor of 3 roughly. Yeah. Here the residual, these are both, oh no, it's the same, yeah, they're same axis. It's just that this one is very asymmetric, right? Because it's starting there, 0, it's going very much positive up to 1500 and little bit negative, but mostly on the positive side. This means that the clay is driving the pile quite strongly downslope and not allowing it to go upslope. Yeah. Here we have this residual value somewhat less compared to this. Yeah. But what is very clear is when I have more axial load, I get this positive side even bigger than that, but also it's more symmetric both upslope and downslope. Because the effect of the clay layer, the amount of load that can apply or force that can apply is relatively small compared to the axial load the pile is carrying. So whether the slope wants to go down or not, it still has to cope with the axial load. So that will oscillate because it got the inertia both positive and negative side that is driving the piles. Okay? Right. So this is experimental evidence. Now, how do we sum up all this? So we got horizontal load, yeah, and we got deflection here. And we are putting data from different tests together. So what you can do is look at where the pile will undergo ductile response, yielding and ductile response, and where will it undergo unstable collapse or buckling type failure. So what we are saying is these are obviously the blue line and red line are idealized lines. The actual experimental ones are in the black. Okay, they're not perfectly like that, but they're not far off. In fact, I would say it's pretty good. So if I make my axial load smaller, then I'll follow more or less the blue line, reach some peak, and I will get slow yielding of the pile, and it will continue to deform as the plastic hinges form because my axial load is relatively small. When you have 3 times more axial load on the pile, it goes up here. First of all, it can't take as much H, undergoes some more deflection as driven by P delta, and then it will fail. It will reach its MP. And once this type of thing happens, it will reach the unstable collapse state. This is what I was saying in, I've forgotten, is it yesterday's lecture where we said we did some abacus things where I'm pretty sure I've shown you this. So if you, in abacus using Rick's algorithm, you can get that kind of behavior. If you want to capture that kind of post-buckling behavior, you will see that I need to draw a circle around here, draw tangents, and then work out my way down here, iteration by iteration, and then you can follow post-buckling deformation behavior of columns. So that's what he has done for the numerical bit, but effectively that is for ego satisfaction, all this. For a practical engineer, once you reach this, as he has drawn here, crash bang, pile dead is about right. Okay? So what we just shown is if you have quite a lot of axial load on the pile, you will buckle, and that is understandable. That's what we are saying. But if the amount of applied axial load is small, you will get this kind of yielding and but stable ductile response. So no sudden instabilities. Right. Then we want to see how we can use this in design. So let's consider a pile, half a meter diameter, length maybe 14 meters. When I say length, length in the liquefiable layer, EI of say 50 meganewton meter squared, round number, MP of about 160 kilonewton meter. Okay, these are the values. So here we are doing the load per pile. So this depends on got 2 by 2 pile group, 2 by 3 pile group, whatever it is, you work out the load that pile is carrying per pile. The group is carrying, but then you work out the force per load per pile. And on the x-axis, we are looking at the force the crust can apply. 1 meter thick crust, 2 meter thick crust, you can work out how many kilonewtons that it will generate. So I can go along here, and let's say I got something like 6 kilonewtons of the crust force. Then I can go up and see I can almost apply 900 kilonewtons of axial force, still not buckle. So this line marks the buckling line. Okay? If my crust force is more, then this value will come down. So very quickly you can check that will this cause me buckling or not in one figure. Yeah? Because this is not buckling in what you have done, where everything was level ground and it's all liquefying. Now you are in a slope with a non-liquefiable crust on the top. Yeah? You can also check what the pile deflection is, delta, compared to the load you're applying per pile. So, for different crust forces, 6, 18 and 30, 6, 18 and 30, these are plotted. The instability is about there. So, clearly we don't want to go as far as that. So, you can see, say I'm applying 400 kilonewtons force. So I can come along here and see for a crust force of 6 kilonewtons, I'll get a deflection of maybe only 0.02, something like that. If I apply 400 kilonewtons, but my crust force is 18, I'll get deflection of 0.1. For the same thing, if the crust force is higher, I'll come down to about 0.18 meter. So we can say how much, depending on the crust force, we are deflecting the pile. Yeah? And we can also plot, I think there should be one more. No. Okay. This is the crust force here, deflection here, but for different levels of axial load you're applying. I haven't done anything. अरे यार, ये तो बेकार है. Hello. ठीक है. I mean, we're almost done, but thanks for the trying anyhow. If not anything else, it's quite amusing. So here we can see how these crust force and deflection get influenced by axial load. This work, as I said, is nearly 10 years old. Neither the Japanese nor the Americans, I don't think, fully understand what this means, and therefore it hasn't made its way to courts of practice. But it's been published. People read it. Other academics in the US and in Japan talk to us, call us, email us, and oh, that was good. How do we do this extra thing or something else? But really, what frustrates me is that the same old things keep getting circulated. The Hamada equation of empirically calculating the movement, when we know Newmark method works better, or this is a complete process. We know the failure mechanisms, we know what are the important factors in this, and here is the data to support it. You can't ask for more than this, and hence the reason for the GIAN course is that at least you guys know this all exists. You may not pick up all the nuances of what is being presented here, but at least you can go back and read the papers, right? You can read the book, read the papers, and so on. But be aware that it is all there, and it's can be used straight for design. It's not something we made up. Now you can say, how will all this change if you've done this for zero point 0.6 meters or 0.8 meter or 1 meter diameter pipe? Okay, if what happens if L changes and so on? Yes, this gives you a starting point, right? So then you can say, well, I got longer pile, then obviously my P crate will become more critical. That's common sense, right? I got more stiffer clay crust. The force F crust will go up. So you can at least as a first point of for design do that. Okay, very good. So I'd like to summarize with this slide where basically piles in laterally spreading soils suffer quite a lot of damage because of this kinematic loading imposed by the flowing soils. This is very clear. You got inertial load, but you also got this kinematic load, which is where we started all a few days ago. Single piles were investigated. We shown the inadequacies of design methods like the JRA 1991. Recently, I've been in Japan. They said, "Oh, we got 2015 JRA code." So this is all old news. I went and somebody gave me a copy of the new code, and I looked at the new provisions in the new code. They're exactly same as that. They changed the date of public. The closer piles will act as one large pile and rotate. Piles that are widely spaced will attract the flow of the soil. They almost act like single piles. The main point I wanted to convey, and this is really the crux of the matter, is you cannot take piles in liquefiable soils and demarcate them as ones which carry axial load and ones which are subjected to lateral spreading. It's the same pile carrying the same load. So you need to consider the combination of axial and lateral load, and that obviously can push the piles either towards instability in one case, or if you design them more carefully, that should give you push the pile more towards stable yielding. And obviously my design recommendation will be try and design your piles to suffer more stable yielding is always a safe design. In unstable collapse is never is. Okay, right. I think I entertained you suitably for today. It will be almost a crime not to ask you to do anything. So what I like you to do is to do this calculation where use the same, you have access to these charts, right? So use exactly these, yeah, but so EIMP values are given there, and apply an axial load of half a meter, right? So 40 times 4. 160, 1600. So that's fairly lightly loaded pile for that diameter. Okay, and the slope, let's keep it the same, 6 degrees. And so work out, so bending moments. So I'm going to say, do you use CU or SU for underhand strength? CU is okay? Okay. CU of 50 kPa, and that thickness is 2 meters. Okay? And this is all going, I'm going to call that also 14 meters to match that. 14 meters of liquefiable soil, 2 meters of crust on the top. So work out the bending moments and tell us what the factor of safety against failure is. So bending moments, factor of safety against plastic collapse. Okay? Eh, do you think you need any other information other than that? All good. If you feel you're missing some information, make assumptions and just write what the assumptions are. Okay? And I think Professor Agnihotri already said tomorrow you need to submit all the bits I asked you over the last 3-4 days. Very good. We finished ahead of time today. But there should be enough work for you to do. Yeah.
What was the residual force? There was a residual force plus transient force. What exactly is that residual force?
Residual force is like once the clay has failed, you got to the peak, yeah, or even for liquefied soil, you got to peak, and once the displacements are quite large, right, it can't. Initially, when it starts to move, it applies big pressure, and as there is more and more displacement, the force it can apply comes down, and that's what that down thing is. The Go and Rourke have that. What is the peak value? I think about 15% of mean confining stress, dropping to about 3% of the mean confining stress over a very small range. The thing is, it drops from that peak to residual in very small displacement. So the strains are very small.
Cyclic forces were there, which is corresponding to the gravity.
Yes.
And then there was a residual force one, which is
Oh, you mean in these ones? Yeah, yeah. No, no, this is just removing the cyclic component. Yeah, maybe I didn't explain that properly. So he marked it as residual, but basically what this is you form the cycles about a mean value, right? So this is what that mean is for that cycle. So say you got 1 point here. You look at where did that cycle go, there and take the average.
how the mean is important to us.
You take the max and min and take the average. It's just you are removing the cyclic component of it.
So the displacement will be proportionate to the mean.
Yeah, yeah. Because otherwise the cycles are going back and forth. You need somewhere you need to anchor your point. Yeah, yeah.
So in this, if we are having more extra load, it is not getting soft.
More extra load is showing it is not softening. Basically, what it's showing is if you put so much axial load on the pore pile, no matter what the clay does, everything is dominated by the load on the top. And that's why it oscillates like mad. It probably fails the clay both on the downslope and upslope side because it wants to oscillate both sides, but it got all that GPA, gravitational potential energy, the mass on the top. So that will push anything in its way, and poor little clay ain't going to do anything. Okay, that's what's going on there. Okay, anything else?
There was some PL in your derivation of limited premium.
Yep.
There was a question PL.
Yeah.
So how to estimate this PL?
Well, I thought that's what you're going to do. You're asking me to solve my problem. You have various ways, right? One way is go back to the Go and Rourke. Yeah. Because that is the curve they have shown. You can pick from there. Yeah. One option. Other option is this one. Look, I'm not going to tell you how to solve the problem. You have a go. If you can't do it, we will have a go tomorrow. Otherwise, what's the point?
Then one general question.
Yeah.
Like before liquefaction, suppose we have some properties of soil. We have particular pH curve, we have a number of internal frictions. Now, during liquefaction, these properties will change. The pH curve will be something else.
Yeah.
Then psi will almost be negligible. And then after liquefaction, will you get back to original properties?
I mean, post long time after liquefaction. Are you talking about post consolidation?
Like after earthquake, after a week maybe.
Yeah, yeah, okay. Yeah, you're talking about post reconsolidation after the liquefaction. The belief is yes. In fact, if anything, you'll get better because the if it is sand, it would have densified, right? So you'll get better resistance than before. During liquefaction, one of a current project we are doing is we got a monopile, we liquefy the soil and pull the monopile through the liquefied soil before the pore pressures are dissipated. The results are yet to come, but that's something we are trying. But I think I showed you the data for before and after liquefaction in one of the centrifuge tests. That's the paper we published in Bulletin of Earthquake Engineering. The chap is called Seong, Abadi, myself, and Haig. You can look at that paper. So we clearly post liquefaction reconsolidation, the lateral capacity of the monopile increases because the soil has densified. All right? Anything else? Very good.